Welcome back to this online lecture series workshop on understanding the science behind geological hazard for early warning and mitigation. There has been some rescheduling for due to absence of one of our faculty, and but anyway, nevertheless, all the topics will be catered to by other faculty members. The last one here in this slot was supposed to be dedicated to earthquake hazard, seismicity, and geophysics. So Dr. Chatterjee will cover that part, and that he will take from 4 o'clock to 4:30, and maybe slightly beyond that also. So be prepared to be here in online mode say, till 4:45. Be ready for that. For some time from now, suppose next 20, 25 minutes, 30 minutes, we will discuss about a little bit more about the landslide that I feel that is left there. It is basically the first part of the landslide lecture. Generally, I take that way. So where we focus on developing, focus on the mapping aspect, like development of sustainability, vulnerability, risk map, etc. So, as per the definition, as I've told you in the morning, that vulnerability is basically is the capacity of the social, physical, and economic structure to withstand and respond to hazard events. In a way, what I mean here is that it takes care of all the elements present. The elements can be road, the built-up area, the agricultural land. So these are the elements. If I can make a kind of map from that, so that becomes my vulnerability map. Sustainability map, on the other hand, is your uh, is basically the all the causation or causative factors taken together, like slope aspects, geology, geomorphology, distance to lineament, drainage density, SPI, TW, all those which basically keep the slope ready. So that is my sustainability map. And combining these two, we have the risk map. We are familiar with these definitions. Now, the first stage in this, when you are into the landslide, doing some research work about the landslide using satellite data. So first thing is that you have to prepare an inventory. Inventory, like many other things, is basically the polygons, active polygons of your presence of landslides. So wherever on surface you can detect a landslide, so you can make a KMZ or shape file out of that, and these shape file put in a single GIS layer will be called my inventory. This I am doing basically for the monitoring of the assessment purpose. Then once I come to the vulnerability sustainability and risk, so we are at still assessment and mitigation only. This we have discussed how the landslide look like. So finally, the hazard zonation map will look like something like this. This has been made long before, maybe 30 years back from now, and that is still valid. And a lot many updations is available on this. This shows that this is the Kedarnath temple we have discussed a lot in this morning. This is the temple, and around this we have all my high or very high zones still there. So how do I prepare this kind of map? This particular portion of the lecture is dedicated to that. So how do I make it on using satellite data on a GIS platform? So first, we have to look for the sources. So landside inventory as such, we can take use from, we can generate the KMZ shape files seeing the data. The data can be simple cartosat data, list-spot data freely available, or even better, that is available in Google Earth platform. So those images on the Google Earth we can see in 3D, and then we can delineate the area where landslide is actively present. Mind it, that is an active landslide map, GIS map, and that has a time connotation. So 2025 December, I have made the map. Maybe 2024, 26 December, there will be different map, because in between we have the monsoon season, or 24, 23, 10 years back, the map where inventory map was different. They can increase, they can shrink, they can change their dimensions. So that's how the inventory is always time stamped. So you have to, the moment you make an inventory, you have to tell that it is from which data. Next is your vulnerability mapping. Vulnerability mapping, for that we have to take care of the settlement, the built-up areas, the road fields. We'll add this upon and make the vulnerability map. For the sustainability, I have told already, slope aspect, geology, structure, stream, soil depth, vegetation, geology, all these layers. The operator is free to decide more than these layers, or he or she may omit some of the layers depending upon his or her need, depending upon the area. They're all site specific. So maybe some area, if I know that slope is more prominent, more influential in terms of landslide occurrence, so I do not consider other layers because that is going to dilute my result. And in some cases it may happen so that I am not aware of the area, I have not gone to the field, so these many layers are there. In addition to that, also I add a stream power index, I want topographic wetness index, all these also is to be included. Why? Because I'm not, the operator is not confident that with how many layers I get the actual picture of the susceptibility. So that's why as many layers as possible I consider. So that's how it's site specific, it is operator specific. Right. And basically what GIS exercise, what GIS weightage we give, the algorithm that I follow has been described here. There's a beautiful slide that tells you that these are the layers, so thematic layers. So distance to stream, relative height, slope, aspect, vegetation, all these layers, if I put them together, I get a sensitivity map. But how do I get it stitched together? So that is the algorithm part. So in algorithm wise, what the GIS, ArcGIS or QGIS software is doing, that we need to understand. These are, as I have told, they are all causative factors, conditioning factors. They basically are keeping the slope ready. They are called, each one of them are called a class. So within the class, suppose slope class, we have 5 classes, 0 to 15 degree, 15 to 30 degree, like that. So 5 slope subclasses are there. So each class here contains some of the many of the subclasses, many subclasses. So we have to understand that which subclass has more, which subclass has what type of influence in landslide occurrence. But how do I know that? One way of doing this is that doing experiment. What experiment we are going to do here? We will cross this slope layer with the inventory layer that we have initially made. Inventory is what? This layer where the landslide polygons are there. So this inventory layer, if I combine with this slope map, if this map and this map is combined together, the sandwich product or the resultant product, what it will be shown, it will have the attribute table of this raster image will show that which subclass of the landslide, subclass of the slope layer slope class will have maximum of these landslide polygons, because this has suppose 6 subclasses, and obviously if I stitch these with the inventory layer, then there may be a situation that where suppose 15 to 30 degree content, 30 degree slope class coincidentally contains many of the landslide polygons. So that means in a way we can say that these 15 to 30 degree subclass is somehow responsible in landslide occurrence. So that is the inference we draw from here. Similarly, we can stitch this relative height with inventory, stream to distance with the inventory, aspect with inventory, just to understand that each subclasses within this class, how much influential they have in landslide occurrence. So that basically why we need to know the inference. The inference is basically gives me idea about, while applying the algorithm, while applying the GIS operation, it gives me idea about how much weight is to be put to which subclass. Well, ultimately the subclasses are responsible for landslide occurrence, we have understood. So the subclass that contains in a class, the subclass that contains maximum number of landslide polygons obviously has to be put with maximum weightage, and less other subclasses are not that important. So that is what. So we have to suppose we have this 5 1 2 3 4 5 for 9 classes, and each suppose on an average contains 5 subclasses. So 9 into 5 is 45 subclasses are there, which are in a way or the other is responsible for causation of landslides. So 45 subclasses are to be given weights in the algorithm. So we have to derive then 45 weights, and each of these are assigned to the subclasses, each of the subclasses. So that's how we get the weights now. Now, once we cross this inventory with this stream, inventory with the slope, this cross product are stacked here again. So there are 9 classes. So there will be 9 stacked layers. Finally, what we do, we stitch again these 9 layers together to get the sensitivity map. So each pixel in this, there are numerous billions of pixels. So pixel here in this subclass tells me what? Tells me information about the distance in distance to stream in meter, relative height in meter, slope in degrees, aspect in degrees, like this. So each pixel. So each pixel here contains information about the weights that is arising out of subclass, all the 45 subclasses. So each pixel supposedly it has information about the 45 weights. Now the operator is free to define a threshold. So how to go with the threshold? The operator decides that 70% threshold rule is something that we go with for this region. What does it mean? It means that whenever highly influential weights are coinciding together for a particular pixel, if the 70% of them are coinciding together, that means they are more influential. So the weights will be initially calculated weights will be either positive or negative. If suppose out of these 45 positive negative mixed subclasses for a particular pixel in your susceptibility, 70% of this 45, suppose 23, 24, 24 positive weights are merging together for that particular pixel, are coincident with that particular pixel. So that's why they pass that 70% threshold rule, and the software understands the most of the influential factors are here concentrated here. So that's why it's very landslide prone area. So the software gives a red color to this. Similarly, we give next step, we give 50% weightage. That means out of 45, 50% of the subclasses, if the 50% of the subclass means 22 subclasses are having positive and they are coinciding on that pixel, they will be given, they are passing your 50% threshold rule. So that means they are moderate. So they will be given a yellow color. Similarly, suppose 10% less. That means 10% threshold means all out of the 45 subclasses, all my negative values, 19% of the negative values are coinciding together. Only 10% of the positive values are coming together. So that's why it can cross only the 10% threshold. So likewise, that will be given the safe area because negative values are mostly there, 90% negative values. So that's why the pixel is supposed to be given your green color. So now each of the pixels are color coded. Now the operator asks the software that please classify this. So what the software does, the software depending upon the nearest neighbor calculation, it sees the wherever red pixels is wherever red is there, and generally in nature it happens so that if some pixel is supposed to 10 meter here pixel size. So 10 meter pixel within the 10 meter your redness will not vanish just like that. This is the vulnerable area is an area. It's not a pixel. So you have a congregation of red pixels that is given a red color. It appears as a red zone here, green zone here. So it's classified in that way. So this is how the inventory layer looks like, where all my active landslide and all of stabilized landslides are put together, and they are kept in a fashion so that you can see them valley-wise. Wherever there is a river bend, they are occurring. Wherever there is a drainage in coinciding, the landslide inventory is occurring there. Landslide presence is there. Just to given visual estimate. For the vulnerability, I told you that we have to take cues from the element. So here the building is there. So this building, we prepare a map. Or suppose a road is there. The road, building, all these taken together. So, sorry, road is here. So this is my road. That is my road. The roads we take a separate GIS layer. Agricultural land we take separate GIS layer, and these layers are added together. This is a settlement, road, and agricultural land taken together gives me a vulnerability layer, vulnerability map. So in this vulnerability also this classified. The classification says it has 5 classes, very low to very high. So very high means the red zone, red color it has given like before. What does it mean? That means, and please see the red zones are coming all along the road. So while adding this, I have given maximum weight to the road layer. Getting so road layer 0.5% weightage and 0.25, 0.25 I give to these two layers. So if I add this weighted mean, weighted average of these 3 layers, I get a map like this. Right. Similarly, for the susceptibility, if you remember, there are different classes. These are my subclasses, and from suppose we get 45 subclasses. So these are my total 45 subclasses, and putting together these we plot their weights. So all my each of these vertical line represent one subclass. So 45 subclass suppose we have, so 45 vertical lines are there, and this is the zero line. So that means above zero, whatever the vertical lines are there, they are having my high influence layer. So high influence 0.74, 0.76, some of the figures have been circled there. So these subclasses are particularly meant for responsible for landslide occurrence. There are several other layers which are not responsible. Please see, they are not responsible. So that means that these layers, these subclasses will not have any role in landslide occurrence. So that is, they are more in number compared to this positive one. So that is why in a layer you get many of the regions are green. Most of the regions are green, only few are red. That is because your subclasses that are responsible, and with this 70% threshold, they are few in number. So that's why red areas will be few. The comparing, if you compare the total green area versus total red area, the red area is only quite less, but they are extremely important to know that where the landslide probability is there. This red zone consists of numerous pixels, and as I have told you, each pixel coincidentally contains, by 70% rule, it contains positive values from those 45 parameters, 45 subclasses. 70% of them contain positive values. So that's why they are given a red color. And the congregation of these red pixels are giving me a red zone. So that's how we know that this area is landslide prone. In 3D, we can show it like this. And then obviously, if you prepare a map, it's not the end. You have to validate this. Any GIS prepared map has to be validated on ground. So how we can validate this? There are different ways. One is RUC UC curve. That basically deals with the true positives and the true negatives. Just to get rid of the alpha and beta statistical error. True positive and true negatives are what? So you go to field, you go to this area, collect samples, you stand, suppose you're standing on a landslide, you take the lat long, correct? So standing on a landslide means that is a true positive, landslide is happening there, they are the true positive, and some area purposefully you have to take where landslide is not there. Suppose on agricultural land, or suppose on a pond, on a lake, no landslide can happen, a plain land, so there are your two negative points. Collect suppose 25 such points set file from those areas, and some from your landslided area that you can physically verify on the field. So these 50 point from your true negative points and 50 true positive points, you have to give it to the software, and software based on that the true positive and true negative will be compared with this map. Try to get your validation points, true positive and true negative, that you gather from field from all around, right? It's not that this area only you concentrate and you get all data from, because the software, what it does, it will consider the true positive and true negative, then it compares the true positive and true negative ground truths with this prepared map and give you a value wherever there is a pixel match with the positive to positive, red to true positive, and green to true negatives. There has to be a match. If this match doesn't come properly, if there is a disruption in this precision, then what will happen? Your ROC issue value will come low. That means they will have low accuracy map. But suppose you have prepared a good GIS map considering all layers, and your true positive and true negative data also is authentic data, that you have ground validated data you have collected, and then you plot it. The software will plot those points on this map and see where your true positives are matching. How many of your true positive field collected true positives are matching with these red layers, and how many of the true negatives, field collected true negatives, are matching with your green layers. So suppose 90% match appears in both the cases, then the accuracy, average accuracy will be 90%. But suppose there is a 70% match. That means either the true negatives or the true positive, they are not matching exactly. So that basically tells, because ground data is field validated data, that cannot be wrong. Then there is it references that your map, something to do with your map. Your pixels red pixels and green pixels have not appeared correctly. So the accuracy has to be increased. How do I increase the accuracy? After preparing a map, you have to go back to the basics. You have to check which layers you have taken for susceptibility. These 9 layers. Did I miss anything? Or suppose one or two particular layer was most important, others were basically diluting the thing. So omit those layers or give them less weights. Getting? Or suppose I have taken only 5 layers and I've taken on 5 layer and getting a accuracy assessment done. So maybe the operator has to take should have taken more than 10 layers, 15 layers. All possible aspects should have has not been considered. So then also your map will not be correct, and you will end up with your low accuracy. Your true positives and true negatives collected from the field will not match with your finally prepared hazard generation map. So that is how we do this. All right, I have, I think. Yeah. Yeah, side by side, if I see, I think I'm close to the this particular session. So vulnerability, susceptibility, and then we cross this, we get risk. I told you risk is a big thing, so that simply means that if risk is high, both the susceptibility and vulnerability separately and equally, they have to be high. So that's how we get a risk map. We did it for other areas also, like Jamunotri area, which tried to do where from Jamuna River originates, and this is from the Kedarnath area again, but this is quite recent. They are post-disaster. So that's why the susceptibility map also has to do with the timing. Which time you are preparing the susceptibility map? Maybe in later time, the map will not be useful that much. There will be because some addition of some layers or the layers that you are using for that map, layers have changed itself. LULs have changed. Geomorphology have been modified. There is an earthquake someday comes up, and the lithology also changes. The possibilities are there. So that's why periodically you have to update value at that. I believe I have ended this part. Thank you so much. We'll move to Dr. RS's earthquake one. Thank you so much for attending this.
Okay, good afternoon, friends. I am back again, and almost at the end of the workshop today. So today, as we already told you, and this coordinator, Dr. Chaturaj, has already told that one of our faculty is stuck up in Delhi due to this cancellation of flights, but that is not an issue. All are here, all are experts. So this last session, that is on essentially on earthquake hazards. So that is seismotectonics and active tectonics, then seismic hazards, seismic hazard analysis, and particularly this your co-seismic and interseismic, this your deformation measurements, using particularly the geodetic, this your techniques like your differential interferometric SAR, and sometimes GNSS also, GPS. So we'll cover most of this your part, and some part has already been covered in the previous sessions. Okay. So here we'll also cover bit of geomorphic analysis of active tectonics and neotectonics. Okay. And geophysical investigations. That is very much part of these sessions. Okay, let us start. Yeah. So, this earthquake, all of us know what is an earthquake. So it is caused by sudden movement of a subsurface fault, and the energy which is released, in fact, that was stored as strain in the rock. Okay, that when this stress exceeded the limit and strain exceeded the limit, then this energy is released. So it is converted to seismic waves that in the morning also I have discussed. Okay, that is the elastic rebound theory. Okay, this energy is released in the form of seismic waves, okay, which radiates from the earthquake focus. Focus is the origin of the earthquake, okay, source of the earthquake. So this or the beginning of the rupture, okay, in other way. So these seismic waves cause this ground shaking, and this can be measured by seismometer. Okay, but all these waves are not going to make these damages, as I told in the morning. No, this is surface waves are the most destructive. Now, this can be measured by the seismometer. That is, it has been shown here. A three-component seismometer records P and AS waves from a local aftershock of the Killary Latur earthquake, a old one. Okay, is that I have just picked up how it has been measured. Okay, this is how the seismic waves are measured by the seismometer. Now you see in earthquake, this is very important. All of us or many of us, we know that is the focus and the epicenter of an earthquake. The the source of the earthquake or the beginning of the rupture, as I told you, that is the focus, and the epicenter is the point directly above the focus on the surface is the epicenter. And this starting point of an earthquake below ground, where the faulting occurs, is the focus. Now you see these earthquakes, this impact will be the strongest is at the epicenter in and around that. Okay, sometimes where the rupture is exposed. Okay, so in general it is weaker when it go away, but sometimes the rupture propagates and it exposed at some distant locations. So at far locations, but there will be these damages can be high where the rupture exposed. So that is important. Now you see how this earthquake, this your strength can be measured. Particularly earthquake strength can be measured in two ways. One is what is the energy, that is the magnitude. How much is the energy released, and what is the this damage potential, how much damage it does after the earthquake occurs. So this earthquakes measured based on three different scales. So here the first scale is your magnitude of the earthquake, and the other one is the how much the earthquake causes the damage, okay, the effects or the damage of the earthquake. There is another way of doing that. That is the third way of measuring the earthquake is the total energy released by the earthquake. Now you see a seismograph is used to measure the strength of an earthquake, and it produces this your seismogram. That is the this your the output of the seismograph. So that shows the amplitude of the earthquake. Okay. Now in this magnitude scale, this earthquake is scaled into 1 to 10 rating. Okay. So this is the amplitude of the earthquake. So 1 to 10 rating. That is on the Richter scale. That is one of the scale for measuring the magnitude of the earthquake. There is another measuring this style or technique, that is the moment measure. I'm not going to that details. So moment measure is basically how much is the slip the earthquake caused, how much is the surface area of the rupture. Okay, all and this that is multiplied, then you will get the total this moment. So this is moment based magnitude of the earthquake. Okay, so but the other way of measuring the earthquake is the intensity of the earthquake. That is the how much damage it causes. So the effect of an earthquake on the earth surface, that is called the intensity. And the intensity scale consists of a series of certain key responses, such as people awakening, the movement of furniture, and whether the people feel it or not, whether the windows, glasses or window pane, they are breaking or not, whether the chimneys are damaged, okay, or this different intensity, and finally the total destruction. Okay, that is the maximum this your value in the scale, that is 12. So it start with 1 when only detected by the seismographs, by the instrument only, but not by the human being. And then 1, 2, 3, 4. In some cases, even if it is very weak, there are some animals can this feel, but this human being cannot feel it. Okay, we can feel only when the magnitude, intensity is substantial. So now when it is 6, for example, okay, then it is felt by all. Okay, but it does not cause much damage, but it can be felt. Okay, when it is 6, but up to 5, it is not all can detect it, and sometimes animals can detect even it is much lower than that. Some animals. Okay, and what I told you that 12, when it is 12 means it causes the total destruction. Now this is the scale. I'm not going to the details that you can get from the any this your the internet search or Google search, for example, you can see this, what is the intensity scale, what it means from 1 to 12. Okay, when 1, 2, 3, 4, 5, like up to 12 means to total damage. Okay, this complete destruction. So now if it is, for example, this 9, 10, that means also there are substantial damage has happened. Now coming to your tectonics part of this earthquake, that is the science of the earthquake. So now you see this plate tectonics is very, very basic for understanding the earthquake origin. You see there are 7 major these lithospheric plates, and many minor lithospheric plates are there for the earth. And this I'm not going to name each one of them. It is I have mentioned here in the Australian, Eurasian, African, North American, like this. Okay, and there are minor plates are there. Now what is important here in plate tectonics is the plate boundaries. Okay, plate boundaries are basically the zone of maximum earthquake occurrences. In fact, from the geographic locations of the earthquakes, okay, where the maximum earthquakes are happening, from the geographic locations of that, if you draw the lines, so basically you can outline this, what is the plate lithospheric plate boundaries. Okay, so depending on the occurrences of the these earthquakes, one can outline the lithospheric plate boundaries. You see this your statistics of the earthquakes. In general, there are thousands of small earthquakes occur almost every day globally. I mean, there are thousands of earthquakes. Those are of very small magnitude, 1, 2, 3, something like this, up to 3 or 2.5. These are considered as small earthquakes. So they occur every day. There are thousands in number. But medium to large earthquake, where the magnitude is 6 to 8, this is medium to large, that on an average globally, once in a month, this earthquake occurs. And the strong earthquake, where the magnitude is more than 8 or close to that, that occurs on an average 1 in a year. Okay, so but there is the great earthquakes like even greater than 8, like 8.5, even up to 9, they are very, very rare. Okay, now you see this this nature of earthquakes or the magnitude of earthquakes are controlled to a great extent by the plate boundaries. And you know there are 3 types of plate boundaries. No, there one is convergent. The plate boundary are subduction zones, where the one lithospheric plates going inside the another lithospheric plate. This is known as the subduction zone. So here this which is going inside the other plate, it is destroying. So one plate is going to be destroyed, another one is above it, isn't it? So this is the region of the plate boundaries known as convergent plate boundary. These are the source of the large earthquakes, and they are different in general. Whereas these transfer faults, where these 2 lithospheric plates slide past one another with respect to each other. So this is the source of the medium to large earthquakes. And the spreading ridges or the divergent plate boundary, where the 2 spreads are spreading apart. Okay, they are going apart from each other. These are known as the spreading ridge, where the crust is created because the melt is coming out. So this is the source of small earthquakes. So here the magnitude is very, very less. Now here we need to understand this tectonics. There are 3 different this time domains or time scale of the tectonics. One is in general we call it tectonics, where we analyze the large scale deformation and earth evolution processes at the scale of hundreds of million years. For example, the tectonics in the Precambrian time, the Precambrian tectonics, for example. But neotectonics means the tectonic which is new, neotectonics. Okay, the age wise it is quite young. Okay, so neo represents the age term, isn't it? So few thousands to 10,000, so tens of thousands, not 10,000. So few thousand to tens of thousands and even up to millions of years, this neotectonics represents. In fact, the present day lithospheric plate configuration, when it gets settled down, or the jigsaw puzzle, no, these all the lithospheric plates are moving with respect to each other, and the present day configuration of the lithospheric plate, what we see today, the lithospheric plate configuration, when this particular jigsaw puzzle, when it is solved, as you know, analogically, these children plays with this your jigsaw puzzle, and when this everything is matched well, so then this puzzle is complete. Like this, when these lithospheric plates are moving with respect to each other in different directions, when the present lithospheric configuration, when it has achieved. So this is the this your time limit for that particular area. Like in case of India and the Himalayan region, it is around 50 million years when the this Indo-Australian plate is collided with the this your Eurasian plates. Okay, when just collided. Okay, so then this lithospheric plate boundary has been settled down, isn't it? So from that time onwards, whatever the tectonic activities has happened, that we consider as the new tectonics. But active tectonics means what is presently operating, what is happening today. Today means not just today itself, it's tens to hundreds of years and may go up to the thousands of years. Okay, so this includes this co-seismic and interseismic deformation, what is happening this now. Okay, so for this geomorphic expression exists, and you know the geomorphic expression what remains intact. It is on an average, it is up to 10K, means 10,000 years. One can see the what is the landforms, what has been developed 10,000 years back. In general, it again it is a function of what is the climate of this area, particularly the rainfall and the temperature. So if it is a dry area, it may the landforms can be retained for even more than 10,000 years. And if it is a very high, strong, the humid tropical climate, a lot of rainfall happens, temperature remains high. So in such cases, it may be even less than 10K. Okay, this is just a general this year observation. Now you see some of the this active tectonics, this your the features. You can see here you can see the highway, this how this offset you can see in the road itself, isn't it? Similarly, you can see similarly you can see in case of this your deep sleep motion here. Okay, just what you see this here the triangular facet and this where is the this offset in the this your ridges you can see, isn't it? So that is basically because of the deep sleep fault. Just it's an urgent phone call. Just a few seconds break I'm taking. Okay. That I will discuss. You are going to apply. So sorry for this interruption. So I have shown you this. There are two this illustration. One is a stack slip fault of the active tectonic, this stack slip fault, and this is the deep slip fault active tectonics, where you can see the offset of the mountain ridge. Okay, there's the topographic break. And now see this is the in case of San Andreas fault, how the river this you're subjected to offset. And in fact, it is happening continuously time to time. The river offset from this to this. And again, there will be previous course of the river. You can find even the site. Okay. So there is the this when the river offset you find. So definitely it is very recent. Okay. So this can be considered as the active tectonics. Okay. Similarly, here you see that there are some kind of shearing has happened in the northeastern part of the India and in Meghalaya state of India. Here you see the river is showing straight this this rectilinear trend, isn't it? And here, just if I show you this, yeah. So you can see this is the soil infilling all along this line. and the river got this trend rectilinear, this very anomalous straight length. And also you can see the vegetation cover in this area, so showing this bend, isn't it? It got bent here. Okay, there is a bending of the vegetation cover from this and this. Okay, that is what interpretation is something like this. There is a fault, or this shearing has happened. When this is operating, this the movement is, this side is towards this and this side is towards this, isn't it? Similarly, you can see this is the thrust fault, and this one block is riding over this another, isn't it? So this is I have taken from the this the internet, this figure. You can see this on the hanging wall, that is the riding over this foot wall block. Okay, this basically a thrust fault. You see, this is not only it is moving or riding over this foot wall block, but also there is, due to this this unique movement, there are the fault propagated folding is also happening. This is the fault propagated fold. Similarly, there are many other these landforms. There are characteristics of the active tectonics similar to that what I have shown you, that there is the this your topographic offset, and you will find this alignment of the springs and these triangular facets. Here in this case you can see triangular facets are developed, and this your these springs can be there where the this aquifer is cut at number of locations. Okay, so this is you can see, and flat irons also, in sometimes when the beds are dipping this opposite to this your fault line, then you can see this your flat irons. Here you see in this in the very close to Dehradun. In fact, it is the near to Saranpur area where you see this. There is the active tectonic fault. You can see here, isn't it? In fact, it is what I have told you is not close to Saranpur, but it's very close to Dehradun. It is basically Mohand, okay, in the region. Okay, so here you can see how this your fault plane here, and this is the Sibalix, which is riding over. This is the this IGP, Indo-Gangetic Alluvial Plain. This is the riverborne deposits, and this is the fault plane. And here this is the Sibalic rock. So this is riding over, and this is the fault plane, which is basically the Himalayan frontal thrust. It represents the Himalayan frontal thrust. And in this Doon Valley itself, very close to Dehradun, we have number of active faults where the topographic this your break in topographic offset. You can see the topographic break here while along this. Okay, in the Piedmont region. This is in the Piedmont region. So Piedmont region, if you find there is some topographic break, so that means that there is some the tectonics happened very recently, because in the Piedmont region there is the material is loose unconsolidated material, isn't it? So this because of the physical processes of weathering and erosion by the running water essentially. So this gets leveled up very quickly, maybe some tens or hundreds of years, it will be leveled up. But when it remains this topographic breaks still visible, that means it has not happened long back in the past. It has happened only maybe some tens of years or hundreds of years back. It's not much. Okay, it is not very old in thousands of years. Okay, so these are these your evidences of active faults, and here this is the example. You can see here the archaeological evidences. This your past houses, those are getting buried, and you can see the bricks of those houses. And this is the locations. Kujnawar is the name of this location. Okay, near Chudmalpur area. You can see the bricks. This one particular age, and these bricks of another age. These two bricks, their characteristics are not the same. So there had been houses here, settlements here, and it got buried due to the earthquake or tectonics. Again, people after some years or tens or years or so, people again make their settlements here and with these bricks, and again it got buried due to the earthquake. So repeated earthquakes or tectonics are causing the damages or burial of the houses. And now presently above this, there are the recent houses. Okay, so it should be safe. Okay, there should not be no more tectonic, but essentially this is the region. No, this is the foothills of the Himalaya. That is all very, very tectonically active. Okay, so and this tectonics is originated from the near the about 100 kilometer from south of this HFT. That is near the high altitude zone or this micro seismicity belt in the Himalaya. That is almost 100 kilometer from the Himalayan frontal thrust or from the frontal boundary. Okay, so which is basically the very close to the junction of the main central thrust and the main Himalayan thrust. That is the detachment plane and the main central thrust. So in transition zone is the zone of the major large magnitude earthquakes or great earthquakes. So from these earthquakes, what is happening? This rupture is propagating, and it is finally rupture is getting exposed in the foreland region. Okay, so HFT is considered to be the this rupture of the great earthquake happened in the this transition zone. Okay, this is the exposure of the MHT or detachment plane, main Himalaya thrust. Now coming to this geomorphic, this your analysis, multi-temporal geomorphic analysis, particularly drainage analysis if you do. So you can make a drainage map of 1972, 1990, and 2003, what he did, and now presently we have prepared one more drainage map of very recent time, and we see that there are some kind of drainage migration happened. Drainage does not remain static at the same time. So what does that mean? So there is some this your tilting of the drainage basin exists, and this tilting has happened due to this tectonics in this region. And even at this moment, there are some active tectonic movement that maybe the slow creep type of movements are happening. Even today, there are slow creep can be observed from these techniques like interferometric SAR. So active tectonic movement are reported, and we have observed by our analysis. So this from the drainage anomaly, if you observe here, you can see that three different drainage line from 1972, 1990, and 2003 at different colors we have represented. You see that how the drainage line has changed, and see this all along this line, the drainage has shown this sudden change in the direction from these two. Suddenly there is a nick point. It is moving towards this your east, isn't it? The drainage was flowing down towards south, and then it is moving towards east. So all along these nick points, there is a major structure is considered to be there, exist. Okay, and you see there are archaeological evidences can be plotted. For example, at A and B, there are the archaeological remains, very prominent archaeological remains we have observed. Okay, at A and B, and so all along that there may be a major tectonic structure. So there is longitudinal fault exists, that is named as the Piedmont fault. You see, this is what you can see in A and B. Here you see this is very close to Roorkee. Again, here you can see the potteries and the bricks, which is buried at this moment. Okay, and the other one is this on the Kuznawar that I have already shown to you. Now in crustal deformation model and earthquake, there are initially there are two-stage model exist. There are crustal deformation. One is the strong motion of earth crust and fault rupture, that is the co-seismic deformation. Another is the slow motion and the strain accumulation and elastic behavior of the earth crust in between these earthquakes, that is the interseismic deformation. But nowadays, we are working with this four-stage model of crustal deformation. Okay, and this elastic deformation theory explained that instead of two-stage model, so four-stage model is more convincing. So these two additional stages are like, one is before the earthquake happens, that is the pre-seismic phase. Another is the after the earthquake happens, that is the aftershocks, that is the post-seismic phase. Okay, so foreshocks and aftershocks, that is the two more your stages has been added in the 4-stage model of crustal deformation and earthquake. Now here you see there are different kind of spaceborne geodetic techniques exist, and there are some kind of ground-based techniques exist, like electron distance meter, then observation GPS or GNSS, then the satellite laser ranging, then very long baseline interferometry, differential interferometrics are, traditional differential interferometrics are, then advanced differential interferometrics are, that is a time series, this deformation analysis, and the scan-search interferometry with the large swath interferometry. Then your DGNSS, similar to the same thing as well, the GPS or GNSS, differential global navigation satellite system, and satellite-based gravity anomaly. So these different techniques have different spatial and temporal scale, which is very clearly shown in this particular illustration. Now you see one of the very important technique nowadays is used synthetic aperture radar interferometry or INSAR. See, this is the technique used, okay, for measuring the displacement due to any earthquake, strong motion, or during the interseismic period when the slow movement is happening. Even the slow movements can also be detected. Now see, what is the principle of this technique? It is the interference of phase of 2 or more SAR images over the same area, and from these two images, both the images have amplitude and phase. With these, we measure the phase difference of these two images, and from this phase difference, your path difference is calculated, okay, and from this path difference, the topography relief, and particularly for this particular session, what is important is the surface displacement can be measured from the wavelength of the radar image, okay. In this case, that is spatial baseline is also important. So spatial baseline and radar wavelength is important. From this phase difference, we can measure the how much land surface displacements happened. And here you see, in case of INSAR, this image, output image is known as the interprogram, which is the pixel by pixel phase difference image. And here in this, when the phase difference is complete 2 pi radian or one phase cycle, so this one complete phase cycle represents the unit of interferometric measurements, and it is known as a fringe, and it represents 2 pi radian phase difference, and it is equal to lambda by 2. Remember, lambda by 2. So radar wavelength lambda by 2 land surface displacement of the pixels or group of pixels along the radar beam direction or radar line of sight. See, in interferometry or difference interferometry, in case of interferometry, this terrain does not move, isn't it? So whatever the phase difference we get from the two images, it represents the distance between the two pixels, horizontal distance and the vertical distance. So it is the horizontal phase and the vertical phase. But in case of this your difference interferometry, that terrain movement is also measured. So in that case, if you take one image today and another image after some days with some time difference, so during that time the terrain has moved. And how it has moved? Because of certain your events like earthquake, like landslide, okay, or slow movement like land subsidence, isn't it? So during that time, the terrain has subjected to some kind of movement. So now from this phase difference, you can subtract this horizontal phase difference and vertical phase difference, then you will get the your displacement phase or movement phase. And that is the purpose of this your technique in this particular session. So we need to calculate what is the phase difference due to the movement of the terrain, so that from this phase difference we can get how this terrain pixels has displaced due to that particular event of earthquake, or during interseismic period, how much crustal deformation has happened, and what is the nature of this deformation, whether it is a strike slip, it represents strike slip displacement, or it is a thrust movement, or it is a normal fault movement. Okay. Now this is how interferometric processing is done. I am not going to the details of the processing steps. And here precision is a few millimeters. So it is sub-centimeter level precision you can achieve in this displacement of the Earth surface due to earthquake or due to interseismic deformation. Now see, this is the first ever image of difference interferogram that shows the deformation, land surface deformation due to an earthquake. So this is the pioneering study of the difference interferometric Lander's earthquake. This causes the land surface displacement. That was published in Nature, and it was shown for the first time that how due to an earthquake the land surface gets displaced. You can see these cycles, that is the fringes, how it has geometrically oriented. It shows that this movement due to this fault is a strike slip movement. And here you can see this is the white lights. These are represents the this your phase offset, and this basically represents the rupture. Okay. Similarly, here in this case, this is a composite interprogram, and here in one side of this area, this fringes is showing this closed fringes, and this fringes shows that the land surface has gone down. Okay, whereas this area, this block remains intact. So that means one block is going down with respect to the another block. And here is this your fault plane is dipping towards that. So that means it is a normal fault earthquake. So this hanging wall has gone down with respect to the foot wall, isn't it? And again, this is also you can see for the co-seismic slip of the south dipping thrust. So this we have seen, one is strike slip, another is normal fault, and in this case a thrust fault. So this area as going up with respect to the other block. This here the co-seismic slip of the south dipping thrust. So thrust is dipping towards south. Okay, and but they did not reach the surface. But this part is going up. So this is basically the hanging wall is going up. So this is a thrust fault. So just I have tried to show these three different kinds of movement from the pioneering studies on the different intercontinental sharp. Like you see in case of Bam earthquake, Iran, that magnitude was not very high, 6.15, but depth was very, very less, shallow. So if the depth is very less, the damage is much. As well as it depends on also these what are the material in the terrain, what kind of material is there. If the material is very hard and compact, then the effect is less. If the material is loose and consolidated, then the damage is much. And in fact, there is 43,000 deaths and 85% buildings were damaged. Okay, here the insert processing can be done. And this is the first interprogram, raw interprogram, then it is the difference interprogram, and this is the displacement, this your vectors due to this earthquake. For Nepal earthquake, so that is what I have perhaps discussed in the morning. So 7.8 magnitude earthquake occurred 80 kilometers northwest of Kathmandu city. Okay, so here is the this main shock, and is the aftershock, 7.3 magnitude aftershock, and see all the aftershocks are aligned in this particular direction. Okay, and there is very less number of aftershock or no aftershock in the western side, but only in the eastern side. So it says something very, very unique. Okay, and all the damages happened only towards the eastern side. Okay, so this is how the rupture has propagated, and finally the rupture is not exposed to the surface. That is also very interesting. So you see, this is the interprogram. Okay, this is from L band and this is from C band. C band shows much more detailed these displacement fringes. Okay, so but what is important here, mostly it highlights this your uplift part. This area has been uplifted, and the uplift is about 1.65 meter, approximately 1.7 meter uplift, and here the subsidence are about 60 centimeter on the northern part. But here this uplifting part is very, very detailed pattern of the uplift you can see, and the subsidence part is not so prominent here. That is C band, radar set 2. Now you see this is allows 2 for this main shock, and it is for the aftershock. 7.3 and 7.8. So the affected area is much more, and the number of fringes are also much more. Here the total displacement is 65 centimeter uplift in the southern part, and here the subsidence is 35 centimeter. Okay. Now see how we can interpret where this the possible rupture zone, because rupture is not exposed to the surface. So we need to understand how the rupture is hidden underneath, remain blind. So where could be the rupture? Because that is very, very important to derive this. What is the peak ground acceleration? How it can be estimated? From this the location of your epicenter, how the PGA values, peak ground acceleration the values are varying with respect to in situ conditions and with respect to the geometry of the earthquake and the location of the rupture. So for that purpose, the rupture line is important. So we have interpreted the rupture line either this or this. Okay, this is the maximum displacement axis, but this is the your interface between the two types of displacement, as well as this is the center of the aftershocks, or the concentration of the aftershocks. So this is the likelihood location of the rupture line, which is hidden underneath. Yeah, this is what we have interpreted. Now, see this based on this MMI intensity, that is the modified Mercalli intensity values. So you can see this is the main shock, this damage, and this is the main shock and the aftershock damage, and this is how it has affected the Indian part that we discussed in the morning, isn't it? Now we can integrate all the in situ conditions and PGA values and in situ conditions, liquefaction potential all together. Then we can integrate all these together and we can find out what is the potential this damage area. So this is the potential damage. Okay, this what are the areas, what is the risk of damage, and this is the what is the observed damage. And you can see both are very much agreeable to each other. So that is why this kind of seismic hazard analysis is very, very important. That seismic hazard analysis you can do before that, and based on that you can do this seismic micro zonation. So at the large scale, if this you can prepare this kind of maps, then you can tell that this is the area where the maximum damage can take place because of the in situ conditions. Okay, in situ geological condition, this is the sediment thickness, this your discontinuity planes. There are a number of parameter topography. Okay, all those things are very, very important to understand where the peak ground acceleration, how much it will be enhanced, and what is the extent of damage it can happen. Along with that, what is the area, how it is more prone to liquefaction hazard, or liquefaction hazard risk is very, very less. Depending on that, you can integrate and you can prepare the potential damage or seismic microzonation map. And this is the actual intensity of damage happened due to the Nepal earthquake. Now, this when studying the geodynamics of the Northwest Himalaya, we need to study the small geodetic observations, both interferometric SAR and the GNSS. And nowadays, you know that this your core stations or permanent GPS stations network has been established by ISRO of India, although we had by different organizations like Indian Space Research Organization, then NGRI, National Geophysical Research Institute, then Wadi Institute Himalayan Geology, then MOES. There are many, many organizations. They have their own these core stations, but these numbers was very, very limited number. Now, ISRO of India has been given this mandate to have this network of core stations, and at this moment they have 1,200 plus core stations all over the country. And all along the Himalaya, there is a dense, comparatively dense network of core stations has been established, and those core station data is available to anybody from the government of organizations, and also from this your PSU and this your private organizations can also access with some conditions are there. So you can access this data and you can get this how much is the this strain is getting accumulated, which the area of maximum strain accumulation, that kind of spatial analysis you can do. And along with that, this interferometric SAR is a very proven technique for analyzing the this geodetic this deformation. So in this case, Himalayan in north-south transit, we have studied these different profiles, and we have seen how much is the uplift has happened, and also what is the horizontal this your this slow deformation is happening. So both we have studied. Here you can see the profiles all along the north-south stretches we have studied, and we have identified some of the important locations where the maximum uplift is happening. Okay, like in and around the MCT, for example. And this is the ITSZ. There are also some subtle uplift we have observed. Okay. Then we can also see in regionally how this strain accumulation is happening for this large swath, this cancer interferometry that we are studying. There are many other organizations have initiated this kind of study. Okay, so and people are trying to find out the areas of this your deformation. So this is the how this interseismic deformation is happening, where the strain accumulation in terms of uplift, in terms of this your this how much slip is happening. So this kind of detailed analysis is being done using this interferometric SAR, and which is integrated with this your course data. Okay. So again, this with this your GNSS observations are very much being done by many of the groups, including this ISRO, ISRO, and this IIRS. So we have analyzed a number of locations. What is the course data and this compare mode GPS data. And here we have integrated with that this lineament-based principal stress directions. So from these lineaments, we can identify, or we can determine, rather we can determine the principal stress direction. And we see that all along this area, so at from south to north at different locations near the foreland, so the boundary at and around, in and around the HFT, and towards the north, like MCT or so. So we have this derive this, what is the this principal stress direction from the lineament orientations. So first we have identified the lineament orientation, then we have identified the what is the on an average what is the discontinuity plane orientation, and then finally depending on the this your this sigma 1, sigma 2, sigma 3, we interpret with the respect to the geometry of the this your fault, and then this is the principal stress direction we have derived. This is the principal stress direction, determine orientation of the lineament, and the principal stress direction or plate motion we have identified. That we have compared with the this what is the plate motion we observe from the GPS observations. So these two things are compared. So this is what our study, and then this morphotectonic analysis, what we have already told you. So you can see this kind of this your subsurface features. Okay, so that we have already discussed with you. And here the geophysics or geophysical investigation like ground penetrating radar is very, very important and proven technique to get the subsurface profile, the interface in terms of the dielectric interface, or the where the active faults exist underneath, that can be interpreted. Like here you can see this is the HFT, underlying there are the IGP, that is the riverborne these deposits, and above it there are the siblings. Okay, and this interface, the here this here the you can see the scarp surface where if this from the section you can see it very well, but even if you don't see it from the ground penetrating radar, you can see the geometry of the fault. So this is how geophysical investigations have been working. So in a number of locations we have studied that in the foothills, particularly all along this Piedmont region and Piedmont alluvial region. So number of locations all through the Northwest Himalaya we have studied with the GPR, starting from the northern part. This is, for example, this Haryana, even up to Punjab or close to Jammu, but mostly in the this Haryana and this your Himachal Pradesh and Uttarakhand, up to this your Haldwani fan area, all along this belt from east to west, all along the HFT, and south in the Piedmont region and Piedmont alluvial region, we have geophysical investigations. Okay, and from that we can see that how in the foreland region the deformation, nature of deformation, and the geometry of the not only the Himalaya frontal thrust, but also there are the active faults which is occurring in the Piedmont region, like Piedmont fault, and number of strike slip transverse faults. With this, I conclude and this session. I think with this, our